to introduce Zhang, who's visiting us from UNLV, where he was finishing up his PhD. He's done a lot of really diverse work on protoplanetary disk modeling, from detailed observational work to convolutional neural networks. And I think he's going to tell us about a subset of this work today.
Okay.
And I'll just make it enough. There's also a schedule that was emailed out by Serena, so Shangjia is around this afternoon and tomorrow too. So if you still want to meet with them, there's time on the schedule. So just sign up.
Okay, I guess I can start. So first, thanks to Serena and Caitlin for hosting me and letting me to speak here. Today, I'd like to talk to you about how to probe young planet populations using self-consistent disk thermodynamics. So let's start with the Let's start with this kind of images in the background. And these are protoplanetary disks, and they are the forming site of young planets. In order to study planet formation, we better to understand those protoplanetary disks. Specifically for these around 20 disks. Oh, okay. Oh, yeah, exactly. Sorry. So I was just doing it. These disks are observed by D-sharp survey and at very high angular resolution. And you can see that most of them have the so-called substructures or annular gaps and rings. And there are also some other substructures. For example, here there's an arc, and here there are spirals. But the most common features are the asymmetric gaps and rings. To date, we have observed more than 100 protoplanetary disks in relatively high resolutions, and we find that these kind of gaps and rings are very common. So you might wonder what causes these substructures, and there are so many mechanisms, more than 20 of them. But today, I'd like to first focus on the planet disk interactions because it is the only confirmed mechanism. In PDS-70D, we have very high confidence level of detecting two young planets, PDS-70B and C. And this mechanism is so very versatile. I mean, as long as you tune the planet's location, you tune the planet's mass, and also the disk property, you can almost feed all the observations, all observed substructures. But of course, there are so many other mechanisms. For example, I will talk about the vertical shear instability, which is a pure hydrodynamical instability that can operate in the outer region of protoplanetary disks that belongs to these hydrodynamical processes. And I will also talk about the dust processes. Specifically, I'll talk about the dust thermal feedback later in this talk. So this talk will be separated in two parts. The first one, I will talk about some basics on planet disk interactions, and then I'll tell you how to use these relationships to probe young planet populations using substructures and also using machine learning mechanisms. And in the second part, I will show you some thermodynamical effects on substructures, both for planet gap opening and non-planet origins. And finally, I will talk some prospects on radiation hydrodynamics and its relation for the implications for the future observations. And basically, this is what I'm doing right now and what I plan to do in the near future. So let's start with the first part. This is a quite typical planet disk interaction simulation. The planet is fixed here, and here the planet mass is around a Saturn mass. And the planet can launch a spiral, and this spiral will exert a torque to the disk and open a gap. But the gap cannot be opened indefinitely because the disk have viscosity, which tries to close the gap. And there has been many studies previously on this gap opening process through linear analysis dating back to 40 years ago. But if we want to study the nonlinear process of this, we need to run hydrodynamical simulation. And most of these simulations were done using the isothermal assumptions. There are two very important components in the disk, similar to most of other astrophysical objects. The one is the gas and the other one is the dust. The gas can feel the pressure, so it orbits at a sub-Keplerian speed in the disk. But the dust does not feel the pressure, so it orbits faster and orbit at Keplerian speed. This makes the dust feel the headwind and can drift inward in the protoplanetary disk, unless there is something called pressure bump, and it is what happened here when you have a gap. At a pressure bump, there's no pressure gradient because you experience a pressure maximum, and the dust can be trapped here. But the trapping efficiency is also highly dependent on the particle size. When your particle size is very small, you can see that the morphology of the dust is more or less the same as the gas. But the big particles are very efficient trapped at the gap edge, so you'll see more prominent gaps and rings. And if you observe this kind of big particles at ALMA wavelengths, you would expect something like this. And let's see more trends. First, let's just put a very, not very massive planet, 11 Earth mass planet here in a relatively inviscid disk. Here, the viscosity is 10 to the negative 4, and it is relatively inviscid. And if we increase the planet mass, we can see that the gaps become wider and deeper. And here, if your planet is very massive, 3 Jupiter mass, your gaps become eccentric. If we now increase the viscosity, you can see the gaps become shallower at the same planet mass. And there's similar trend for H/R, or disk scale height, or the temperature of the disk, but it's not as dramatic as you're changing the planet mass or the disk viscosity alpha. If now we look at the dust, you can see the contrast becomes much more, and this is just due to the dust trapping. And if we increase the dust size even further, you can see the rings become more prominent. And this is because the larger the dust size, the better they are trapped at the gap edge. And now if we just focus on part of these simulations, specifically those simulations with very low viscosity, alpha equals to 10 to negative 4, and the planet mass is around 0.3 to 1 Jupiter mass, you can see there are some clumps at the location of the planetary orbits. And they are exactly the horseshoe, the Lagrangian, the dust clumped at the Lagrangian points, L4 and L5 points at the planet's orbit. And they are separating around 120 degrees. Luckily, we have observed this kind of thing in real observations by Long and O in the calcium 15. You can see there's a clump here and there's an arc here separating almost 180 degrees. And this also has been observed in PDS 70 recently. So this can be very exciting because it is an independent way to constrain the planet mass, location, and disk viscosity. Just back to our parameter space study. After having those 2D images, we can azimuthally average those 2D images to 1D profiles, like something like this. And we have around 500 of them. So then we can feed the relationship between the gap width and the planet mass with the combination of other parameters, such as the viscosity and H/R. We can go back to those disk images and using those gap width to feed the planet mass. And these orange dots are the potential young planets inferred from the D-sharp sample. As you can see, there are not a lot of them, and they are also occupying a completely different parameter space as the existing mature exoplanets. Most of the planets are located between 10 to 100 AU, and this is due to our resolution and sensitivity. And many of them have Neptune to Saturn mass. There is only one giant planet beyond 3 Jupiter mass, which is sort of consistent with the direct imaging campaigns. But there is a problem with the D-sharp sample, which is that is very biased on bright and large disks. And this bias was by intention because D-sharp stands for disk substructure at high angular resolution project. And the purpose of this program was to observe as many substructures as possible. So that's why we picked deliberately the largest disk among all our disk sample. But in order to study the characteristic young planet population, we want to study a more representative disk, which is much smaller disks. Luckily, we have such a survey, which is the Taurus survey by Longfeng in 2018 and 2019. And this survey covers the full range of disks around the stellar mass earlier than M3. But there is also a problem for this sample, which is the resolution. The resolution of this survey is not as good as D-sharp. Among all 24 disks observed around the single star in that survey, only 12 of them has been observed with substructures. The rest of them that were classified as smooth disks were, not surprisingly, all compact disks. But still, we have something to boost the resolution, which is to feed them by directly into the visibility plane. And then we can get some more substructures from the wiggling in the visibility. Using this method, we identified 6 disks that have been identified as smooth disks in previous paper with new substructures. And this can boost our statistics. We then use the same linear fitting method in our 2018 paper to put the potential young planet population for the Taurus sample on this planet mass semi-major axis diagram, which effectively doubled the number of potential young planets. And we see that they are actually occupying the exactly or very similar parameter space as the D-sharp sample. Most of them are Neptune to Saturn mass planets located between 10 to 100 AU. And we can do one more thing than the D-sharp sample for this sample, because the disk is more representative and less biased. What we can do is to count the number of planets at each planet mass semi-major axis bin and calculate their occurrence rates. And this is what we got. Here, I just use a very simple occurrence rate definition, but we also have other assumptions in our paper for other definitions. I want to emphasize that even though these 2 different planets populations, the young planet populations and the mature planet population occupy the very different parameter space, but if we compare their marginalized distribution as a function of the planet mass, we can still compare them with mature exoplanet statistics. They are actually quite consistent within 3 sigma, both for microlensing, direct imaging, and the radial velocity surveys. But the consistency should be in part due to our small sample statistics. But we still have some hope in future, because if we have the NGVLA coming online, which is the next generation very large array that can give us much smaller angular resolution. And on the other hand, we can expect the Roman telescope can give us a lot of microlensing exoplanets at much wider orbit. We will have the chance to observe this kind of 2 populations at the same parameter space. Yes, question.
Yeah. So when you're comparing with all of these different populations, you're obviously doing an extrapolation.
Yeah, some of them have extrapolation, for example, the RV, but the direct imaging and microlensing for those, I could compare directly like as function of the mass, but they are not at the same location.
Right, but you don't have the same. I mean, you didn't show detection or your candidates that were 10 Jupiter masses or something like that, right? So you're extrapolating in planet mass, either up or down, to get and then integrating, right?
I do have a planet with like a 10 Jupiter mass here, and I'm comparing. So for example, for microlensing surveys, they are talking about the planet mass stellar mass ratio, and then I will just use the planet mass stellar mass ratio to compare with those statistics. And for direct imaging, they are comparing about the absolute planet mass. So I just used the absolute planet mass here because it's quite simple. Among all the sample, I only have one planet here. So I calculate their occurrence rate is around 4%. And then I can use that to compare with the exoplanet statistics.
I see. So you're not generating a power law
No, not a power law.
to integrate over to get these comparisons. You're just saying if you happen to have 1 or 0 or 2 or something.
Right, exactly. Yes. But for macrolensing survey, what I'm comparing here is actually comparing with the power law that was fed by Suzuki et al. And then I use that power law to integrate the macrolensing statistics at a specific beam, the same as my beam taken, and compare with the occurrence rate with that. Okay, so finally, I also want to mention that we could use machine learning techniques to constrain the planet mass and this viscosity. Because we had a problem with this 2018 paper, which is that we use the 1D radial profiles to feed the planet mass. But the disk has 2D structure at least, but they are 3D in fact. So if there are some features such as the dependency on the disk viscosity can make the disk more asymmetric, and the 1D method cannot probe this. And machine learning techniques can be used to directly feed the 2D images. So what we did is that we ran 150 more simulations generated by the Large hypercube sampling on the alpha H/R and planet mass, this parameter space. And then we do some processing of the image and augmentation. And finally, we feed them using the residual net and did a regression problem for the planet mass and alpha viscosity so that we can get a continuous value of the planet mass and viscosity. And we have very good, accurate prediction. The standard deviation of the uncertainty of the planet mass and the viscosity are all within 0.2 dec. And what's more, I want to show you here is the GradCam or activation map in this plot and this plot. What it represents is where the neural networks used the most to infer the planet mass, meaning that the networks focus the most on the gap region. And this is exactly what we want them to learn. So to summarize, the first part is that we can infer young planet populations from substructures and compare them with exoplanet statistics. But there are two caveats and very big caveats. The first one is that we should assume that all these substructures are due to planets, which might not be true. And secondly, we should also believe that the isothermal assumptions are valid, which is not true. We might not be true either. And what's more, almost all other mechanisms that do not involve planets is also underexplored for realistic thermal physics, because many other mechanisms, people have been just using the isothermal simulations to study them. So it is also good to explore what happened if we use self-consistent thermal physics to study them as well. And this leads to my second part of the talk, the disk thermodynamics. So let's first go over the thermal structure of protoplanetary disk. The thermal structure is very crucial for studying almost all aspects of the disks. It is important for modeling observations because we need to do radiative transfer. And it is also very crucial for disk chemistry because the chemical reaction and the phase transition and anything is highly dependent on the temperature. And finally, I also want to emphasize the hydrodynamical instabilities. For example, the vertical shear instability that I'll be talking about today is also very sensitive to the temperature gradient. So the simplest model for a passive protoplanetary disk is as such. The heating is coming from the stellar irradiation, and the cooling is done by the radiative cooling by the dust. Now, suppose you have a photon sent by the star, it will hit this surface and be absorbed by the dust. And this dust will re-emit at a longer wavelength. And this photon might penetrate to the midplane and hit another dust in the midplane. And then this dust will re-emit emission at even longer wavelengths. And this is typically what we observe at ALMA. With this kind of heating and cooling balance, you should expect a sort of a superheated atmosphere and a cool midplane. And this is what people have been observed recently using ALMA gas emission. Then this is work by Charles Lau in 2022. In our 2021's paper, we want to try to extend this smooth disk structure by studying the temperature across the dust ring, sort of like this. And we identified two mechanisms. The first one is the previously studied shadowing. Suppose now one part of the disk surface is heated up by the star, and it will puff up and block the radiation for the back of it. And then this part will shrink down and have cooler temperature. And the other mechanism that we identified at the ring for temperature variation is this so-called excess cooling. And this mechanism needs two populations. But this is quite normal at the pressure bump, because at the pressure bump, the big particles are more efficiently trapped at the midplane and concentrated at the midplane and also trapped in the radial direction. And smaller particles are more spread out, both radially and vertically. And we also know that large particles have higher cooling efficiency because they have larger opacity at millimeter wavelengths. So with these two conditions, you would expect at the location of the ring, the temperature will be lower and there's a temperature dip. In contrary, for the shadowing mechanism, you would expect the temperature will be lower after the ring, outside the ring, because the ring just blocked the radiation from the star. We can also look into 2D in the vertical direction of our excess cooling mechanism. And here you see a higher concentration of the big particles, and here you see more spread out smaller particles. And the second panel is the temperature map. And you see at the exact location where big particles are concentrated, you have lower temperatures. And you don't see this if you only assume small particles or big particles. And this is also can be observed in ALMA observations. For example, in this MAPS large program, you see that the location of the bright dust rings tend to co-located with the location of the gas dips, temperature dips observed by gas for 3 of these disks. And this kind of phenomenon has also been observed in CI tau. You see here, the second ring of CI tau from the dust is co-located with the location of the temperature dip for the gas emission. And the temperature can drop by 5 Kelvin or so here. But we also want to do one more step. The previous slides only show that the temperature is a static one, and we do not evolve them with time. What was the situation be like if we relax this assumption and let the temperature evolve with time? And there's one very simple prescription for doing this, which is the orbital cooling or beta cooling. The way it does is that you assume the disk has a background temperature or background state, which is represented by this TE rate. And then your disk gas parcel can be heated up or cool off, and it will relax to the temperature, background temperature eventually in the time scale T cool. And this T cool is called the cooling time or the thermal relaxation time. So it is a relaxation problem. And the specific energy you take from the gas parcel is using this prescription. And you can also normalize this T cool by the local orbital time. And that's why we call them orbital cooling. When your big T cool is very small, that means that your temperature will be back to your background state immediately. And if your T cool equals to 0, that approaches the isothermal limit, meaning that you always have this constant temperature throughout the disk, throughout the time. And the other limit is the adiabatic limit. When the disk T cool approaches infinity, that means your disk does not care your background state anymore. The gas will be cooled off or heated up indefinitely. So there also have been so many studies that have shown that this cooling time is varying across disk, from the inner disk to the outer disk, and from the midplane to the atmosphere. If you adopt very simple minimum mass solar nebula model, you should expect very high cooling time in the inner disk and very low cooling time in the outer disk. So in our paper, we wanted to study whether this cooling time has any effects on the gap opening by the planet. What you are seeing here now is the planet disinterrection in the polar coordinate. The planet is always fixed here at r equal to 1 and phi equal to 180 degrees. You can see the spiral launched by the planet. Now let's increase the cooling time. You can see as the cooling time increasing, the spiral becomes much weaker, exactly around 0.1 to 1 orbital times. And more interestingly, these damping effects are weakened, and the normal spirals are coming back when your cooling time is even larger, approaching the adiabatic limit. And this has implication for the gap opening, because with a weaker spiral at this kind of cooling times, you would expect a narrower and shallower gap opened by the spirals. And in terms of observation, you would underestimate your planet mass if you assume isothermal disks. And this orbital cooling prescription is very neat, but we know that this cooling time should be varying in both space and time. So how can we capture that? The only way that I can think of is to run radiation-hydrodynamic simulations. Luckily, we have the tool to do this thanks to Athena++ and implicit radiation solver. This radiation solver is so powerful that it can work at both optically thin and thick regimes. What's more, it can treat shadowing and beam crossing problems properly, which were not possible for methods like flux limited diffusion and M1. I can just demonstrate what is the beam crossing test here. It is very simple physical problem, but it's very hard for the radiation transport schemes if you need a closure relationship. What it does is that you shoot two beams in the space, and physically, once these two beams cross each other, they should propagate in their original directions. However, if you use flux limited diffusion method or M1, once they cross each other, they will merge into one and propagate in the vertical direction. But our implicit scheme solves the radiative transfer equation directly, so we can capture this problem correctly. And then I want to use the vertical shear instability, or VSI, to demonstrate the power of this code. What is VSI, you may wonder. So let's go back to the thermal structure of the disk again. So if we think of the midplane, the temperature near the midplane, we can assume it's quite valid to assume that they are constant in the vertical direction. And now let's just worry about the radial profile of the temperature first. And this is quite common in protoplanetary disks because you expect the hotter temperature closer to the star and the colder temperature away from the star. Once you have this temperature gradient, after very simple calculation, you will figure out that the azimuthal velocity along the z direction is not a constant. And this leads to the vertical shear, or dv phi dz. And this vertical shear is exactly what causes the vertical shear instability. The vertical shear instability also needs very fast cooling, but it can be realized relatively easily at the outer region of protoplanetary disks. Another very classical feature for the VSI is this so-called corrugation mode, or this upgoing and downgoing gas at a very narrow radial extent, but in a very grand scale in the vertical direction. And what you are seeing here is just the velocity of the disk in the vertical direction. With this kind of corrugation mode, you should also expect anisotropic turbulence, because now imagine you have a dust parcel here. It can be stirred up very high up above the midplane to the atmosphere, but it can only move in a very small extent in the radial direction. So for my radiation simulation, I set it up by implementing the stellar irradiation as a ray tracing method, and put it as an extra heating source term. And then I use D-sharp opacity. I assume the dust to gas mass ratio is 1 to 100. And I also use a relatively high resolution simulation in the R theta plane. And the disk mass is 1% of the stellar mass, which is also quite typical. In the next two slides, what I will show you is the streamlines or line integral convolution of the vertically isothermal simulation, and also then our fiducial radiation hydro simulation. The only difference is that the latter's radiation is turned on. And the color of the next two slides will be representing the meridianal velocity. The yellowish color means that the velocity is higher, and the bluish color means that your velocity is lower. And this is what you would expect for the vertically isothermal simulation. And you see this granularized circulation motion in the vertical direction across the disk. However, this is our radiation simulation. After you turn the radiation on, you can see the structure becomes completely different. In the midplane, you see the velocity is very low, and the atmosphere is still quite turbulent, and the velocity is high. Yeah. Sure.
So when you say the only difference is the radiation is turned on, presumably the temperature profile is not the same
Right.
in the two cases.
Right, but the initial condition is the same. But after I turn on the radiation and let the simulation run, the temperature will be different, and the cooling time is also different. So there are a lot of differences.
Right. So I guess when you say the initial conditions are the same, how did you get the initial conditions for the isothermal case?
I just after running the radiation simulation, I measured the scale height at the midplane as a function of the radius, and then I put it and then turn off the radiation and run the isothermal simulation. So this is as close to as I can do. The radial equilibrium, yeah.
But then the temperature evolves away once you allow the VSI to develop?
The temperature is different because of the stellar irradiation. The vertical isothermal simulations have constant temperature across the z direction. So that also leads to a different.
But the initial rate, so it's just the radial. So it's just the radial temperature that is derived from the radial.
Yes, exactly, at the midplane.
At the midplane.
At the midplane, yes. Because I can show you in the next slide that the temperature very near the midplane is still sort of vertically isothermal. Yeah.
So how does the radiation strength vary along the radius?
The radiation strength is just like the power law, like a inverse square power law. But you integrate through the optical depth, so it's also depend on the optical depth. Right. So
how about the density distribution in the vertex scale?
Right.
You calculate the magnetic.
Yeah, the density distribution is also dependent on the thermal structure. for the pure isothermal density, pure isothermal case, if you assume the temperature is constant along the z direction, then you would expect the Gaussian. However, as I will show later, since your temperature distribution is not constant anymore, you actually have two Gaussian. One is the Gaussian at the midplane, and the other one is the Gaussian for the atmosphere.
Yeah, so, well, we're gonna say more about this, but how this result compares with the previous self-consistent radiation-hydrodynamic simulation of the BSR?
It is quite consistent actually, but I don't know why they did not study this in very detail, because the difference between this simulation and the previous red hydro simulation is that I use much higher vertical extent. So previous radiation hydro simulation had like this kind of vertical extent. So they only see this very turbulent atmosphere at the boundary of their simulation, and they did not pay. What?
Sorry, what is this?
C over R.
Oh,
I think the theta in the vertical direction it's like 68 degrees, both above and below midplane. So it is like almost to the polar, but not reaching the polar yet. So you can see that in the midplane is quiet and the atmosphere is very turbulent. And at the boundary between the cool midplane and superheated atmosphere, there's a strong shear. So there are a lot of small vortices forming. And another very different thing is that you don't see this very large scale corrugation mode anymore. Also, turbulence becomes very like smaller happens at a smaller scale. And now let's take a deeper look at the density profile or the density in the vertical direction. Here, the tau star equals to 1 is a very important quantity because this is the where, yes, please.
I'm sorry, Andrew has a question. Do these simulations have a superheated surface layer of the disk?
Yes, it is. This is the temperature profile. You can see that the midplane is quite cool and it is almost isothermal, but the atmosphere is superheated. And this kind of temperature structure is exactly set by this tau equal to 1 surface, because the stellar irradiation can only like shine this kind of region and above this region, and then the midplane's temperature is determined by the re-emission around this tau equal to 1 layer. So the temperature in the midplane becomes cooler. And also I want to mention that the cooling time is varying across the disk, and that leads to this kind of velocity structure. You see the velocity in the midplane is quite low, and yes, please.
So, I mean, how do you translate the idea that your cooling time is, it's not isothermal, so you expect some way to damping, and that should affect the smaller scales, right, and the larger scales. So how do you, what is the explanation for the generation of these smaller scale substructure?
Yeah.
Is actually
Yeah, that's a good question. What I did is that I tried to simplify the problem by step by step. So first, I did not show here, but I also ran simulation with the same background temperature as this, but using the isothermal simulation, meaning that all the cooling time at each location of the disk is 0. And with this kind of temperature structure, I already started to see the structure something like this. This is actually quite not quite surprising, because with this kind of temperature structure, you generate more shear than the shear that you would be expected for the vertical isothermal simulation. So this more vertical shear means more like vortices or more turbulence. And then if I measure or estimate the cooling time, using my radiation model, and then run a pure hydro simulation, but using the background temperature plus the local cooling time varying all across the disk, I can almost like reproduce the result here. So I would say first, the first dominant mechanism that leads to this kind of structure is the temperature structure, and then the cooling time also plays a role. I hope that answers your question, but we can also talk offline. You see this kind of structure is very different from this traditional corrugation mode. We can also see the zonal flow develop in our red hydro simulations. And the exact substructures of the gas profile depends on the inner radius of the disk. And basically this different disk has different stellar irradiation or optical depths. Recently, the kinematic features of the disk are very popular because for ALMA, we observe more and more gas emissions at better resolution and also sensitivity. People use this kind of so-called channel map, which is the intensity at different velocity channels, to infer the existence of giant planets. For example, here, if you have a very massive planet, you expect there's some deviation from a Keplerian plot, which is akin here. And people also try to distinguish various hydrodynamical instability using this method. For example, people would predict that if you have gravitational instability, you would expect this multiple large-scale velocity deviation at the upper region of the disk. And if you have VSI, you had these burst features. But these models are all having this either locally isothermal or vertical isothermal assumptions. What if we, so what's the prediction for our radiation hydro simulation for VSI? It is something like this. I did not go over like the sophisticated synthetic observation that's these two images, but you can see the point. First, you can see the burst features, but you can also see some like large-scale velocity deviation here. So this means if you want to make a very realistic predictions for observations, you really need to treat your disk thermal structure self-consistently. So to summarize the second part, we show that thermal physics is very crucial for shaping the disk morphology and kinematics, either with and without planets. With planets, I show that cooling can change the gap opening process. And without planet, I show that dust structures, substructures can affect the thermal structures. And using radiation hydro simulations, I show that VSI changes pattern completely, leading to very different observational signatures. Finally, I will just use several slides to talk about what I'm doing right now and what I'm planning to do in the near future, and also the implications for observations. Just a week or two before I visited here, I tried to impress you guys by running a radiation hydrodynamical simulation of planet disk interaction. And on the left-hand side, this is the quite classical simulation in 3D with pure hydrodynamic. Here is a Jupiter mass planet after orbiting the disk only 10 orbits. And you can see the spiral launched by the planet. And in the vertical direction, you see there's some disturbance near the planet. And I will show you the radiation simulation evolving to exactly the same time step as the left-hand side. And if I play the video, you can see the spiral launched by the planet. But the first difference is that you see the density becomes the disk in the vertical direction becomes more settled. And this is because now we have the superheated atmosphere and cold midplane, which effectively lower the disk aspect ratio, or H/R. And the lower H/R makes the planet easier to open the gap. So you can see, even with the exactly same planet at the exactly same time, the gaps become deeper. And another difference is that the disk becomes more turbulent. You can see this more flocculent structure at the outer disk. And if we look at the temperature structure, it is also very interesting. For the radiation hydro simulation, you would expect this superheated atmosphere and the cold midplane. And another thing that may be true or may not be true is that you see the temperature is much lower after some distance away from the planet. And this can be due to the fact that the spiral launched by the planet blocked the stellar radiation and makes the region outside the planet with cooler temperature. Yes.
So why are the Vatican non-isothermal for the comparison?
Because I don't have time to run the isothermal.
No, because I would guess that if you run an isothermal case, even you put in time in the radiation hydro, you would get a very similar outcome.
Yeah. Right, but the cooling, like you cannot pre-estimate your cooling time for this kind of very
Yeah, but you're getting like beta 10 to minus 2, something like that you showed before in the BSI.
Yeah.
You can get something like that in this time as well, right?
Right, it is possible.
It's just
Yeah.
pretty isothermal.
Yeah, but for that kind of thing, you cannot handle this kind of shadow problem, and you should run radiation simulation first, or you can just run the RAD-MC 3D to get a temperature structure and estimate the cooling time.
Your radiation is not going beyond, your stellar radiation is not going beyond tau equals 1, so how the spiral is blocking that radiation is
Because I have the radiation transport like taken over by the code itself, so we'll handle the disk it's like self-emission and cooling, and also the shadowing.
Yeah, no, I get that, but to get a shadowing, you need a rays to penetrate all the way to the midplane and reach the spiral waves. But here you're showing that your rays are not really penetrate all the way in. They just go to tau equals 1 and they get distributed in some presumably diffusion matter.
Yeah, I guess that's a first order approximation. There might be some way still like the radiation can affect the gap opening, perhaps through the higher layer, but I don't know. Yeah, I cannot tell you in much detail because I'm not quite confident about this kind of shadowing effect either. So I need to do more study. For example, now the outer boundary of the disk is not very large. It's only 2.5 of the planet's orbit, and you see that this kind of shadow region is connected with outer boundary. So it might not be true. It can be a boundary effect, but what I'm just showing the potential and yeah, trying to demonstrate. But yes.
Yeah, there's another question. How long did this radiation simulation take to run?
It is taking forever, but for this one, I think I used too much rays. So the radiation, how long does it take depends on so many things like resolution. And another thing that people might not be familiar with this kind of code is that you can adopt the different numbers of rays that you want you to adopt. Here I got like 100 different rays, so it takes a lot of time, and I could reduce that by a factor of at least 5, and that can save a lot of computation time. So for this kind of setup, each planet orbit means around like a day. So and I used like 2,000 CPUs to run it. So for 5 days, it's just 5 orbits. So it's very slow.
Okay, you have a few minutes.
Okay, yeah. Okay.
So you want to, I can wait till the end if you're almost done.
Almost done. Yeah, just finished.
I
Yeah,
was-
yeah. Okay. So yeah, but with that kind of temperature structure assumed, this kind of overdensity in the midplane can just be explained by a lower scale height HOR at this region, effectively increase the midplane density. For future projects other than the radiation hydro project, I'm collaborating, actually sort of advising another student at UNLV, Stanley, and we are trying to use the multi-group radiation module to explore the multi-frequency nature of protoplanetary disks. And Stanley just started this project at CCA this week. And we also know that the FINA++ have a particle module, so I can couple this particle module with our radiation module to explore the dust continuum observations. And we can also explore the different geometry, like the misinclined inner disk, which casts a shadow to the outer disk, and how would that affect the disk dynamics. Eventually, maybe disk chemistry, because our radiation hydro simulations can handle the thermal structure self-consistently. And in the for the observations, there are a lot of going on for this kinematics. For example, this ALMA large program, ExAOs, what they are trying to do is to infer the existence of giant planets from those these kinematics. But I would say that with our self-consistent treatment of the simulations, we can make better predictions than just using pure isothermal simulations. Also, there are already a lot of near-infrared scatter light images on the market, but I don't think we have explored them in the full potential, because these scatter light images are coming from the surface of the disk, where they are very sensitive to the disk thermal structure. So our red hydro simulations can do a better for predicting these kind of images. In the longer future, in 5 to 10 years, we should expect the NGVLA, upgraded ALMA, and ELTs to come online. And we have shown that we have the potential to observe the gap carved by just the Earth's mass planet at 3 AU, and they can be observed by NGVLA. And this means that we can probe the terrestrial planet forming at habitable zone in near future. This is similar for the upgraded ALMA and also ELT. Basically, I'll just leave my summarized slide here. What I show is that isothermal simulations has already helped us a lot to constrain young planet populations. But if we want to make the most of current and future more dedicated observations, we need really to treat the disk thermal structure self-consistently, and better using 3D hydrodynamical simulations to constrain the complex substructures and planet formation processes. All right, thank you so much, and I'd like to take some questions.
I was gonna get the question and a comment. So I mean, I think you got at this a little bit, and some of the questions that Leo was asking, that right, there is a very important distinction between, you know, fast cooling, isothermal, vertically isothermal, and locally isothermal.
Yes.
Those are 3 very different things.
Yes.
So when you're comparing, it's good to be very clear about when you're using, you know, each limit. But then, right, because of course you don't need to run a 3D rad hydro simulation to know that the temperature structure will look like you've seen, right? Where
Yeah.
isothermal and the plane is superheated. But then the thing that that I see is that you aren't reproducing a flared disk. Right, so if I were to like run RAD-MC3D, I would, you know, the typical way, the typical models all start with the Chang and Goldreich flared disk solution.
Yeah, I think it is flared. If you measure the
Okay, it's just hard to see. It looks pretty flat.
right, but if you look at the if you calculate the mid-plane temperature as a function of the radius, the power law is the flared disk. But I don't know, I don't have a good explanation for you, like why the top to one surface is flared. I think basically, I put a lot of structure, like a lot of optical depth inside the simulation boundary, and that's already very relatively optically thick. And I don't know. The tau equals 1 surface is not flared, and the HOVR is sort of flared, at least if you measure them at the midplane.
Yeah, I mean, I guess, but I mean, in terms of what the reason that you would care about HFR being flared has more to do with what's happening at the surface than the midplane temperature. And so I guess, I mean, maybe you can't see it unless you look at a vertical density profile.
Yeah.
Maybe it's hard to tell, but I guess it'd be good to know if you're getting something that is quite distinct from the Zhang and Goldreich solution, because of course that's what people.
I think I think the big difference between this red hydro simulation and just using a static method like red MC3D to calculate temperature is that now you just handle the hydrostatic equilibrium as well, and in a dynamical way. The temperature you see is something like this for our red hydro simulation. But if we just fix the hydro part and do not let the hydrodynamic involve, meaning that we just fix the disk structure and then running the radiation part, we can get the thermal structure exactly what you wanted. But if you iterate this too, like what has been done here, both the density structure and the temperature structure would be relatively different. So that's probably why you don't see the Goldreich, Zhang exact pattern that you would expect.
And just see there, I'm not saying not to do the hydro part. I'm saying that if you knew the temperature structure a priori and the cooling time is fast, right? It sounded like you were saying you could reproduce almost the correct VSI structure.
Yeah.
Without changing gamma. Basically, you don't need an energy equation,
but
a full energy equation necessarily.
Yeah, but the thing is that you don't know the thermal structure a priori because there's a balancing for the hydrostatic equilibrium as well. You can iterate it for the 2D, but in 3D it's hard to do them. For this kind of situation, you can probably iterate the thermal structure of the disk in the vertical direction at each location, and then iterate them back and forth between your vertical hydrostatic equilibrium and the red MC3D, and then you got a sort of structure similar to this. But I mean, still the time scale now you cannot control, and in 3D is even harder.
Yeah, it used to be interesting to understand the limits when it works and when it doesn't.
Yeah, the time's kind of over, but we can continue discussion after this. The last call, if there is a burning question from audience. I guess they can't really hear very well. Right, thanks for the speaker today, and if you want to meet the speaker, there is a sign-up sheet. Please go check the time.